In this lesson, 3.1 through 3.3, our objective is to be able to apply exponent rules and simplify radicals. So just as a reminder for our warm-up, we want a reminder of what an exponent actually is. What is it keeping track of? So when I see 4 to the 5th power, what does that actually mean? So an exponent keeps track of how many times a base is being multiplied by itself. So expanding this would be 4 times 4 times 4 times 4 times 4. So a base times itself 5 times in this case. And that's the expanded. Go ahead and try B. Pause the video, try B, and then check your answer. So the same thing applies here, no matter if it's a variable or a number or a combination of variables and numbers, the exponent is the same, means the same thing. So this time I have 3x's multiplied by itself and then 2y's multiplied by itself. And since there's nothing in between those two, that automatically means multiplication. So those two things are being multiplied by each other. So now we're going to go backwards on this side, and we're going to condense. So we're going to bring them together. It's already expanded. So for part C, we have 3 times itself twice. And then we have x times itself 5 times. And then we have y times itself twice, or just once. So you can write y to the 1, or you can just write y, because that implies if we don't write an exponent, that implies it's to the first power. So again, go ahead and pause the video and try part D. Okay, so this time we have more variables, more letters all combined together, but it's still the same rule. We're still doing the same thing. So there you go. When you are writing an exponent, it is so important to know how to properly write an exponent. So your factors are, in this case, are factors of x. And how we write that is I'm the base. So whatever the base is, it stays on the same level, it's the same size, but then the number of factors that you have becomes your exponent. How many times it's being multiplied by itself becomes your exponent. And please make sure that your exponent is high and small. And you need to be able to obviously see when you're looking at something that has an exponent that it is an exponent without question. So it needs to be clearly notated. So we have the base, which is on a normal level, and then the exponent, which is higher and smaller. And here we go. We're going to start writing our rules. So we have our different exponent rules. These are the names of them, and then we're going to go through each one and come up with some shortcuts. So the product rule, we have a squared times a to the third. It's product because product refers to multiply. So let's expand this and then write our answer. So we have a times a, that's our a squared. And then we have a 3 more times a times a times a. So there's our expanded form. And so now after we expand it, we want to simplify what we can. So here we can actually combine this all together, and that becomes a to the 5th power. So can you see a shortcut? How do I get from this original one to my final answer without having to expand it? So the answer is we just add the exponents together, and you probably saw that already, but let's go over here and actually write the shortcut down. So it's a to the power of 2 plus 3, which still gives us a to the 5th. So we're going to do a generalized rule over here. So if I have any base with any exponent times by the same base with a different exponent, the rule is we can add those exponents together, plus n. So there is our generalized rule. So anytime you have two bases that are the same with two exponents being multiplied, you can add your exponents to combine them. The next rule is the power rule. So this one, let's expand. And so I'm going to expand the outside exponent first. So we have a squared times a squared 3 times a squared. So that's 3 times. And then I'm going to expand all of these individual squared power things here. So that becomes a times a times a times a times a times a. So all together, if I combine this, this becomes a to the 6th power. So again, how can I look at this original expression and just take a shortcut and jump to my final answer? And the answer is, for this one, we're going to do a to the 2 times 3 power. So when you have a power being raised to another power, that is your shortcut. You multiply them together. So let's generalize our rule again over here. So we have x as our base to the m power being raised again to another power to the n power. That becomes x to the m times n. There's our generalized rule. Next rule is the power of a product. So for this example, again, we expand. So we have a b, and that's going to happen 3 times, raised to the 3rd power, times ab times ab. And you can rearrange these, because multiplication you can rearrange. Put all of our a's together. Put all of our b's together. So then when I condense it, it becomes a to the 3rd, b to the 3rd. So there we go. So our shortcut in this case is that we can, when it's a product, we can kind of distribute that exponent to the exponents of all of our factors on the inside of the parenthesis. But this, again, this is so important. This can only happen if it's a product. You cannot do it if there's a plus sign or a minus sign. We can only do it if it's a product. And so we have a shortcut here of, so if it would be a to the 1 times 3, because we can look at both of these as a to the 1, b to the 1. So you just multiply that 3 by the exponent that's already there. So a to the 1 times 3 and b to the 1 times 3. So that exponent gets distributed. So if I have x and y being raised to the m power, I can distribute it to both. So this would be x to the m, y to the m. And again, you multiply if there's an exponent there already. Okay, power of a quotient. So this one, if I expand, this becomes a over b times a over b 4 times. And when we are multiplying fractions, you just multiply straight across the top. So I get a times a times a times a on top, b times b times b times b on the bottom. So then I can condense those. It becomes a to the 4th, b to the 4th. So my shortcut in this one is that I can just do the same thing pretty much as what the previous rule did. So if I'm raising a fraction to a power, I can distribute that exponent to the numerator and the denominator. So that would be it. So I can distribute, so then it just becomes a to the 4th on top, b to the 4th on top. And again, just like power of power, you can multiply if there's an exponent there already. So let's say I have x over y raised to the m power. I can distribute that to both the numerator and the denominator, and they would both get the same exponent. The quotient rule is our next one. So let's expand 4, 5, 6, 7 divided by 3 of these. Now when you have the same factor on top and bottom, we reduce this just like we do a normal fraction. So if I have any common factors on top and bottom, I can cancel them because a divided by a would equal 1, so they cancel each other out. So let's cancel as many pairs as we can find. Cancel, cancel. That wasn't very good. Cancel. And then we write what we have left. So in this case, I don't have anything left in, or I have a 1 left in the denominator, but dividing by 1 I don't need to write. So then I just have a to the 4th left over. So what's the shortcut? And the answer here is that I do a to the 7 minus 3. And that would be my shortcut. So when I'm dividing, it's top minus bottom. So let's generalize our rule over here. So now I have x to the m divided by x to the n. It becomes x to the m minus n power. And don't forget that it's the top power minus the bottom. Okay, exponent of 0. So in this case, if we use the rule that we just identified, this becomes 2 to the 0 power, right? If I do 2 to the 3 minus 3, that would become 2 to the 0. But if I expand it, let's do 2 times 2 times 2 over 2 times 2 times 2. Remember, when I cancel these each become a 1. So that becomes a 1, that becomes a 1, that becomes a 1. So then 1 times 1 times 1 cancels out to be just 1. So if you have anything to the 0 power, it just equals 1. Anything. And that counts for numbers, variables, no matter what. Anything to the 0 power equals 1. So if I have x to the 0, that equals 1. Last property, negative exponents. So if we use our quotient rule on this one, this becomes a to the 3 minus 5 power, which is a to the negative 2. Another way of writing that is if we expand this, this becomes a times a times a on top, and then I have 5 on the bottom. So I cancel just like normal, but this time the ones I have left over are in the denominator, and that makes a difference. Remember, when you cancel all those things, it becomes 1. Each of those becomes 1. So I have a 1 actually left on top, and then if I condense the bottom, it becomes a squared on the bottom. So if you have a negative exponent like this, you can just turn it into a fraction or move it to the denominator, and then it becomes a positive exponent. So if you have a to the negative 2, the shortcut, instead of having to write it all out, would just be to flip it or move it to the denominator, and then it will become a positive exponent. So if I have x to the negative m power, that equals 1 over x to the m. And I wanted to write an additional one. So if I have x to the, if I have 1 over x to the negative n power, that would become, we would move it back to the numerator, and it would become regular x to the n. So it goes both ways. If it's in the denominator, has a negative exponent, it will move up. Okay, simplify each expression. So I'm going to go through a few of these with you, but then I want you to practice and then check your answer on the answer key of the notes. So simplify each expression. So there's more than one way of completing these, but I'm just going to do the way I am used to and go from there. So in this case, whenever I see a negative exponent, I take care of those first. So I move my negative exponents where they're supposed to go and then go from there. So 30 over 5, I'm going to leave those where they are here, and make sure you're only moving the exponent and the base it's attached to. So the negative 2 is not attached to the 30, it's only attached to the x. So now I'm going to move the x to the negative 2. I'm going to move that down to the bottom because it's a negative exponent, so moving it down to the bottom creates a positive exponent. This x is just normal, so I'm going to keep that where it is. This y is normal, so I'm going to keep that where it is. And then this y has a negative exponent as well, so I'm going to move that up to the top. Y to the, and then once you move it, it becomes positive 3. And now I simplify what I have. So now I can use the product rule on these, and I can use a regular simplifying, reducing fractions with the 30 over 5. So 30 over 5, those can both reduce, so I can divide them both by 5. That becomes a 1, that becomes a 6. So next I have a 6 left on top. I can use a product rule on my y's. So y to the 9 times y to the 3rd is the same as y to the 9 plus 3. And same on the bottom, I can use my product rule on my x's. So this becomes x to the 2 plus 1, because that second one has an exponent of 1. So then this final answer, we have 6y to the 12th over x to the 3rd. And that's my simplified answer. This next one over here, take care of my negatives. Except this time, we have a quotient. So we have a power of a quotient this time. So we can get rid of our parentheses first, and then we can worry about the negatives. It's kind of like PEMDAS. So parentheses first, let's do what we can to get rid of those. So if I have a power of a quotient, again, I can distribute that negative 2 to both the top and the bottom. So then this will equal 3 to the negative 2 over x to the negative 2. So parentheses are gone. So we can now move those, everything that has a negative exponent, which in this case is everything. So this, since it has a negative, is going to move to the bottom and become 3 to the positive 2. This has a negative, so it's going to move to the top and become x to the positive 2. And then there's my final answer. I don't have any other bases to combine, and I don't have any negative exponents. It's not considered reduced or simplified if you still have negative exponents. So you just have to take care of those first. Okay, so let's do this one. So same idea, we take care of our parentheses first. So power of a product. So remember, power of a product, we can distribute that 3 to all of the factors that are there already. And we have to consider this as a negative 1 as a factor as well. So I'm going to move that over there as well. So 3x to the 5th. And I'm going to leave it as negative 1 to the 3rd. It's very important that we have that negative 1 that gets the exponent as well. And then we have x squared to the 3rd. And we have y to the 3rd. So again, we still have some parentheses, so let's see if we can reduce those a little bit. So 3x to the 5th, you can leave this as negative 1 to the 3rd, or you can actually multiply it out, negative 1 to the 3rd. So negative 1 times negative 1 times negative 1 is negative 1. And then x to the 2 raised to the 3rd, so we can use the power rule on that one. Power over power, which gives me x to the 6th because we multiply, and then y to the 3rd. And then I have some things I can combine. So I have numbers I can just multiply by each other because they don't have exponents. So negative 1 times 3 is negative 3. And then I have x to the 5th times x to the 6th. So they are being multiplied by each other, so I can add those exponents together. And then I have y to the 3rd. So final answer, when I combine those, I have x to the 11th, y to the 3rd. Okay, go ahead, if you haven't yet, go ahead and print out the rest of these. Try them out or pause the video and try them on your own paper and then check your answer on the answer key. So here we have properties of radicals. Squares and square roots are inverses of each other. Same is true with cubes and cube roots. So squares, like if I have x to the squared and I have a square root, the square root and the square cancel each other out and this would just be x. So same is true with cubes and cube roots. So if I have a cube root, like this is a cube root right here, because we have an index of 3. And if a was cubed in this case, the cube root and the cube would cancel each other and that would equal just a. So those are some properties. And then we also have, if you have the square root of two things that are being multiplied, you can separate them into two different square roots, or roots in general. And you can go backwards. If you have two of the same root, same type of root being multiplied, you can combine it under the same root. So here we go. We are just going to practice simplifying radicals because a square root is just asking us what times itself gives us these numbers. And some square roots simplify really nicely, but others we have to do a little bit of work with. So in this case, what we're looking for is we're looking for, if I simplify this, I get 7 times 7. So I can rewrite this as the square root of 7 squared. And remember, the square and the square root cancel each other, so this will equal just 7. So what we're looking for, we're going to get this square every time we see a pair of numbers. So that's what we're looking for. We're looking for all the possible pairs we can find. Or you're looking for a number that you know the square root of. Some of you just know that the square root of 49 is 7, because 7 times 7 gives you 49. So, for example, in this case, if we break up 24, you can break it up in a lot of ways. So 4 times 6. But some of you know, oh, I already know what the square root of 4 is. But if not, you can keep going. So 4 is 2 times 2. And I found a pair. So I know that once I find a pair, I can take the square root of that, and that's going to equal just 2. So let's keep going. So 6 times 6 is 2 times 3. So it looks like that's all we're going to get. So we have one pair of 2's. So if I'm going to rewrite this down here at the bottom, this radical, anything that you find a pair of can come to the outside, but again, only one of them, because the square root of that is just going to be 2, because the square cancels and we're left with the base. And then whatever you have left is just going to be left on the inside. So again, I guess I can write this separately. So 2 squared, so the square and the square root are going to cancel, so I have 2 left. But then I have 2 times 3 left. So that's going to be 2 times the square root of 6. And that's our final answer for that. So go ahead and break down your number until you find all the pairs that you can. So 2 times 30, there's a pair. So I'm going to find pairs as I go. 2 times 15, 3 times 5, and it looks like those are my last numbers, so I don't have any pairs there. So maybe you can take the shortcut. I have a pair of 2's, so I have 1 2 that's going to come to the outside. And then I have 2 times 3 times 5 left on the inside. So 2 times 3 is 6. 6 times 5 is 30. Again, looking for your pairs. Okay, same thing happens with variables. If I find a pair of variables, I can bring one of those to the outside as well. Go ahead. 2 times 16. 2 times 8. Oh, there's a pair. 2 times 4. 2 times 2. Oh, there's another pair. But then I have one that doesn't have a pair. And I have A. Don't forget about A up here. He doesn't have a pair either. So we put the pairs together. So I have a 2 squared here, and I have another pair, 2 squared here. But then I have 1 2 that's just left on the inside by itself. and I have an A that's left on the inside as well. So this first guy cancels, that just becomes 2, cancels, that just becomes 2, and then I can combine those back together. I have a 2 and an A left on the inside. So we can multiply everything that comes to the outside, multiply everything that's left on the inside. There we go. Same thing happens with the cube roots, but this time we are looking for groups of 3. So breaking this down, I have 2 times 36, 2 times 18, so I have a pair right there, 2 times 9, 3 times 3. And you can pause this if you want to try it yourself first, go from there. Oh, except I made a mistake because I was looking for pairs, and I'm not supposed to look for pairs, because this time it's a cube root, and I have to look for groups of 3. So I do have one group of 3 right here, but this is only a pair, so it's going to have to stay on the inside. Okay, so same idea happens. So if I have the cube root of 2 cubed, that cube and the 3 cancel, and I just bring a 2 to the outside. And then I also have the cube root of 3 times 3 left. So then this would be my final answer. So it's the same rules, but we're just looking for groups of 3. So I'm going to jump to this one, and then I'm going to have you try the rest of them, and then check your answer on the answer key. So 27, we have 3 times 9, 3 times 3. Oh, and this works out perfectly. Okay, but then a to the 7th, I'm just going to bring this down here because I know how to expand that. A times A times A times A times A times A times A. Okay, so I have a group here, I have a group here, and then I have one that's going to be left on the inside. So I have a group of 3s, so I'm going to use the shortcut and just bring 1 3 to the outside. And then I have a group of A's, so I have one A that comes to the outside, another group of A's, so I have another A that comes to the outside, and then I have an A left in the cube root. So then simplified, we have 3A squared on the outside times the cube root